Okay, good morning. I think we should get started, right? We're already late. That's okay. It's okay. So this is the 7th lecture, I think. Morning. So today we will talk about microwave NDE. This is an area that I got into pretty recently, but I have about 3 PhD theses on that. So much of my work will be based on the work conducted in those theses. Okay. Again, the outline, we'll talk about microwave and then how it's applied for NDE, principles governing equations. And then I will present in this application a particular microwave imaging technique that we used. Okay, sorry, the recording or something?
Yeah, it's started.
Okay, so I think these are all some preliminaries. Microwaves occupy this 300 megahertz to 300 gigahertz. That's the region of the electromagnetic spectrum, where the wavelengths can vary from 1 meter to 1 millimeter, right? Okay. Yeah. Okay. So that's microwave imaging, occupies those frequencies of the spectrum. And other property of microwaves is that it can penetrate into dielectric materials. And in it, there are a lot of applications. What we see here is aircraft. Let me use this. It says security screening in airports. Microwaves have been used for biomedical imaging and also for therapy, ablation, heating, and all that. Ground penetrating radar for detecting buried objects, conducting objects. And then also non-destructive testing is in the last 3 decades, I would say, it's been used for in non-destructive. So microwave engineering itself encompasses a number of fields and number of disciplines, like in communication systems. There is a lot of work. Radar systems, aircraft, air traffic control, navigation, tracking, so on. Doppler is used for radar velocity measurements. It's used extensively in the US for speeding, for giving speeding tickets. Microwave heating is used in industrial as well as in homes. And remote sensing, satellite communication, imaging, and all this. Anyway. The basic mathematical description of microwaves is Maxwell's equations, or wave equations. Okay. So you have the Gauss's law, and which are the dot product divergence of these fields are 0 under certain conditions, if there's no surface charge and all that. And then you have the curl equations. And together we can, from these, we can get the wave equation with the wave vector here. And so these are the solutions for the E, and these are all basic preliminaries thing. I'm not going to spend time. Yes, these are, we're not talking about any boundaries or interface conditions. This is in free space, all in free space. Yeah. That's right. That's what I mentioned. Yeah, that's why we have all zeros over here. No surface charge, no surface current, nothing. Okay. So these are just, the things that you studied in your undergraduate electromagnetics class. And I'm not going to do a lot of deep, advanced microwaves because I'm just going to restrict to the concepts that are necessary for NDE. So obviously, when you have any wave process, when energy travels as a wave, you'll have these phenomena of reflection and transmission. And that depends on the properties of the medium. So this is the dielectric, the constants. You have an incident wave, then you'll have some transmitted, some reflected. And those are what you measure and determine the surface conditions. And when you have an angular incidence, and you have this is simply a ray theory approach, and you have Snell's law, which tells you what's the reflected wave and what's the transmitted wave. And one of the things, when you have an infinite medium, you can, just like we had a transformer analog for eddy currents, you can develop a transmission line analog, which is actually at much lower frequencies, but over long distances in transmission line. When you have an AC voltage or current, the equations followed for the voltage and current, if you have if you use this lumped parameter model for your transmission line per unit length, for example, you can you come up with the same kind of differential equations for your voltage and current, and then you can solve. These are all one-dimensional problems, which you can solve for the phasors. That is, if you have, this is the phasor quantity. So V of zt is, of course, V of z multiplied by e to the j omega t. But for any particular t, you can calculate the solutions for voltage and current as a propagating wave in the x and y, z and minus z directions. And also define quantities like characteristic impedance per unit length of the transmission line, or if it is in free space, we also have that, right? So these are all very elementary material, so I don't want to spend too much time on it. So the basic thing, when you study transmission lines, because of the low frequency and the large wavelength, you don't look at the variation in space. You consider at any point it's constant. At any instant of time, the measured voltage is pretty much constant. But at high frequencies, at microwave frequency, you have a wave pattern. What you see here is like a standing wave pattern. So that's what you do when you have a waveguide. And so the voltage or the fields will vary as a function of space. Okay. And you have, concepts like calculate what the power loss and everything. I think you've done that in your microwave lab. So we have seen, basically this summarizes your one of the things that is valid for all frequencies is the skin depth phenomena. So at microwave frequencies, everything is reflected by metals. Microwaves are reflected because there's hardly any penetration. It's reflected, but you can also, therefore it's used from the NDE sense, it's also used for surface conditions. If the surface corrosion, if you have a very thin coating and you want to detect corrosion under that coating, you can use microwave as long as it's all surface problem. Okay. Otherwise, microwaves penetrate, can only penetrate non-conducting or dielectric materials, insulators. It's been used, for composites. That's how I got introduced to microwave NDE, because at Michigan State University, we have a composite manufacturing lab and a composite research center. Okay. So one of the things, any kind of manufacturing, you need to do NDE. So I got collaborate with the faculty there to do NDE of composites. Particularly, one of the things we do at Michigan State is with the automotive companies. Automotive companies want to lightweight automotives, so they want to replace. When you have multiple layers of metal, they want to replace one of the layers by composites, lightweight as well, without losing any structural strength problems. Okay, so microwaves are used for composite structures, also for concrete. One of the papers we have is if you have rebars in concrete structures, that can corrode. And if you want to determine corrosion or the strength in the rebar structures, you can use microwave, look at the reflected wave, analyze and see if there's corrosion. Because, okay. And biomedical biomaterials, because they have very low conductivity, they can be used for, microwaves can be used for that, for imaging different structures in organs, particularly if you have tumors in a healthy organ. The microwave, the electric constant of tumors they've seen at microwave frequencies has a much higher contrast than X-rays. So if you have a tumor, the sensitivity of microwaves is much higher than X-rays, you can determine. But the problem is resolution. Right? You can't detect sub-wavelength tumors, very small tumors. Okay, let's see. So these are microwaves. So microwave NDE, you can, it's like any wave process, you have your sample, you can shine it with microwave using some kind of an antenna or any kind of structure, source structure, and measure the reflected or scattered fields around the object, and then from the scattered fields you can determine a lot of parameters about the sample. As I mentioned, one of the other things also is because EM waves have polarization as an additional parameter. So you can exploit that to get more information about the sample. So particularly when you have carbon composites, you can have polarization along the fiber length for better coupling with the E fields. So you can use it for measuring thickness of coating or layer thickness in stratified samples. In a metal composite structure, you can detect disbond, delamination, or even within a composite material, manufacturing defects like porosities, voids. In laminated composites, you can detect interior flaws, fiber breakage, fiber orientation, fiber crunching. They have a number of manufacturing anomalies in composite structures. It's called fiber bunching. And of course, if there is impact damage. In metals, you can detect surface cracks, surface corrosion, and the big advantage of microwaves. Well, we'll probably I shouldn't jump the gun. I'm going to talk about near and far field. Let's wait for that. And microwave heated thermography is also done. Okay, so instead of using a flash halogen lamp for heating, you can use microwaves. We can very selectively, you can focus heating can be done, and then use thermography. And just like we have laser generated ultrasound. Ultrasound, in order to get rid of the coupling problem, you can shine laser pulses and thermally generate an acoustic wave. And the same thing can be done with microwave pulses too. We have done some work on that also. Again, the advantages is that it's non-ionizing in comparison to X-rays. When you do an X-ray NDE, you have to vacate the place and make sure nobody's around, nobody gets any ionization damage. And it's non-contact again. And you can also do from single, if you have often you have only single side access to a sample, and you can use microwaves for that. And so it's rapid, it's a very large standoff distance if you're doing in the far field. But if you want high resolution, you go into the near field. So let's see, I think the next, please. Okay. don't like these animations. Okay, so microwave imaging, we have basically two modes of operation. One is the far field, and the other is the near field. In the far field, basically, you're a couple of wavelengths away from the sample that you're imaging, but the resolution is limited by diffraction phenomena, right? You have a lambda by 2 limitation. But the electric and magnetic fields can propagate large distances as long as there is not much loss, and you can get information about thick composite structures. The other modality is near field. Near field, there is no limit on the resolution. It's how close, it's the scanning resolution basically gives you a resolution of imaging. So you can go up to sub wavelength, but you have to be very, very close to the sample. Okay. And so basically, you're not even using the wave phenomena, you're using inductive or capacitive coupling with the sample to get some measurements. And so this slide, I think this afternoon, we'll talk about how I can use far field imaging, have the advantages of far field imaging, but achieve sub-wavelength resolution using a lens made of metamaterials. Okay, if you have optical lens, then you really don't get any advantage, but with metamaterial lens, so we'll talk about that this afternoon. That's some work that we have done. Okay, so this slide is basically talks about NDE of composites. I mean, this is how I started working on microwaves because my eddy current technique doesn't work. So it does, for very thin composites, I can run my eddy current signal, eddy current probe at 5 megahertz, a few megahertz, and get some signals. Okay. Or we also worked on capacitive probes, and we can get some capacitive coupling signals too. But recently, with increased use of composites, even in aircraft, Boeing has an all composite. The Dreamliner, which is the 787, is all composites. So NDE of composite is very, very important over there. You have boats and there are wheels, and of course the wind turbines are mostly carbon composite. So we need an NDE method for composite inspection. So some of this shows actually some results that we have got using microwaves. So this is a GFRP sample with 3 different holes of 3 diameters, going from the wavelength to sub-wavelength diameters, and these are some far field imaging, and these are some near field imaging results. Oh, how we do really get it, I'll get into that, but I just thought. Okay. Again, these are some near field imaging results only of a GFRP sample, and you can see some Teflon inserts that we can, that I don't know exactly the experimental details on these. I don't know whether it was, this was not work that we did. Actually, it was from some paper, so I don't have the information over there. This one, I think, was something done in our lab, so we can still see the defective bonding near, but it's all in near field. Okay, don't have any dimensions on that. So right now, what I'm going to talk more about, near field imaging is fairly straightforward. You have any open-ended coaxial probe or anything that you can take and get some near field results. It's no different from an eddy current probe, but it's a different way of excitation. So if in the far field, if I measure the scattered field, how do I go back and image the defect itself? Right, so you have, one of the things, the first thesis that we had was to develop this time reversal methods for imaging of defects. Okay, so the basic idea in time reversal was actually in the 90s, it was applied to ultrasonic waves. And the basic idea is whenever you have a wave equation where you have a second time derivative in time, both for this particular equation, for example, where the unknown is P of RT and P of R minus T, which is in the reverse direction, both are solutions of this equation. So that's the basic principle for time reversal imaging. So we'll see how we can do this for imaging of defects and in NDE. So the basic idea is that when we have, say for example, you have some incident wave and you have scattered wave in free space, and when you have incident wave and you put a sample, or you can call it a scatterer, you measure some phi. This is phi 0, this is phi. And if you have a defect, you'll have another perturbation of phi. Let's call this phi d. If I subtract these two, because these are all linear problems, the perturbation field between this geometry and this geometry is created by a source, which is basically the defect. So the defect can act as a source for the perturbation fields. So that is another critical thing that we use along with time reversal to detect and image defects. Okay, so those are the two things. Time reversal, where I can take a solution, if I reverse in time, it is also a solution of the wave equation. And secondly, any defect is a source for the perturbation field. Okay. So what we do in time reversal imaging for NDE is, okay, here's the source and we take an array of measurements here. These are the received signals. And then we take, we have to, from this we calculate the perturbation parameters. How do you calculate the perturbation parameters? You have to have a calibration sample without defect. Okay, you know what the fields are without the defect, and we calculate the perturbation fields. You time reverse it, and then you propagate it from the, time reverse it, apply the time reverse fields to the receivers and propagate backwards using a model. You can eventually, we'd like to do this in experiment, which it can be done. It's called a time reversal mirror, where you have a source, you have a receiver, time reverse, propagate, and then you receive over here, time reverse. And what happens, it will propagate till it comes to the, it sort of gets amplified. And if there is a defect, it will nicely focus the defect. Yeah. I will do that in the next slide. Okay, I'll show signals. Okay, so once I have the forward model, I take this time reversal signal and give it to the model. And if there is a defect in the model, I don't know if there's a defect or no defect. I don't put anything. It's a clean sample, but the signals have the information of defect. So when you propagate it backwards, if there is a defect, it will come to focus over there. If there's no defect, it will just keep propagating. Okay, so that's the basic idea. So in order to do this, I need a model. So this tells me a simple, for a wave equation, electromagnetic wave equation, we developed a FDTD algorithm. Okay, we developed this whole model. I don't think I'll go to this. It's simply a discretization of the derivative. You take derivative in space and time and replace it by finite differences. Okay, and these are just slides that show you solve for the E field, then you solve for the H field, and at different steps, and combine everything together to get your final electromagnetic field. And of course, you have to apply some boundary condition. You don't want any reflection. Either you have an infinite medium or you have absorbing boundary condition. And I think many of you here have done FDTD model, developed your code, and done this thing. So I won't go to that. But this is the key. You asked about time reversal signal. Should we switch off the light again? I think those plots are not very visible otherwise. Okay, good. So this is the Gaussian modulate pulse that is applied to the input source. And then you have all this array of receivers. Okay. So at each receiver, you will get some signal. For example, this is one of the receiver signals. Okay. A time reverse signal will just reverse it in time. It will look like this. That's all. It's just a simple operation of taking this signal and flipping it. So this becomes your 0, and this is, if this is 0 and 100, this becomes your 0 and 100. That's all. It's a very simple operation. That's time reversal. So each of these antenna signals you reverse in time, and then you apply that to a simulation model, the FDTD model, so it can propagate through a sample geometry which has no defect in it. And then you allow it to propagate, and then you look at the time integrated energy of the signals from each of these receiver array. Okay. So this is the basic idea how I can, if there is a defect, you will see that the signals will come to focus at that point. So the next slide, I think I have some waves, some videos of this happening. You can see that. Okay. Oh, these are again numerical implementation of time reversal. These are the 2D FDTD method. These are the equations that I use for doing time reversal. Again, this is the input signal that is applied, and this is the time domain, and in the frequency domain, this is the frequency content of the signal. Okay. There are two different types of localization, energy localization. One is, as I mentioned, we just calculate the time integrated energy in the received field. So you calculate it as it is coming. You look at the entire time signal at each, at the source and do that. The other way to do a localization is to calculate the entropy at each time. So what happens is when you have a nice diffuse wave propagating, you'll have the entropy will be pretty high. But when there is a focusing action taking place in the sample, entropy is going to be minimized. There is order, right? Entropy is just a measure of disorder. So you'll have, you can look at the entropy curve as a function of time, and then look at the minimas. And at that minimum time, I can plot my electromagnetic fields and see what happens. So it's another way of looking at. Okay. So let's look at this. So this is, I think, why is it not? Hey, this video is not playing. What do I do? It plays. These are all videos that should play, show the focusing action. Let me see if I get out of this mode. Okay, it's playing over here. It's not playing in the. So if you look at, so this is the source. The source is here, there is a metal there, it reflects, and then it goes to the receiver array, okay, and produces the signal. Now, if I look at, this is the forward propagation. If I go to this thing and play this video, basically you're looking at, it's coming, the time reversal signal is coming there, and it comes to focus at the source, okay. So there is no sample, there is no defect, nothing. It's simply source focusing. That's what these two videos show. The first is just the forward propagation to the receiver array, time reverse, and propagate from the receiver array. It does propagate, it reflects over here and comes to this. And so if I take the full signal at the source and integrate, do a time integration of the energy, it will show a maxima at the location of the source. Because right now it's just focusing at the source. And down here, you see the entropy curve. And there are two minimas over here and here. This is the minima that corresponds to reflection focusing at the metal boundary. And the second minima is focusing. So I take the time instant as where the minima occurs. And I plot the field, propagating field, at those two time instants. And you can see at time electric fields at A is the focusing at the metal boundary, and at B, at this minima, it's actually focusing at the source. So you can actually do source localization of the time reversed fields. Okay, so there is no defect, there is no, it's just a source localization. Let's see, I don't know whether there's a, okay, this one is any of these. Oh yeah, this is again a video, so I'll stay in this. So this is now for looking at time reversal for NDE. Here is the geometry. All of these are metal composite geometries. So you have a conducting plate, you have a composite with a disc bond. This is all simulation. There is no, it's not experiment, so we can control everything. And the disc bond is, yeah, over here. There is some kind of epoxy in between composite and the conductor. So we input all the properties of that, and here the source is here. The receiver array is also on the same side because it is single-sided. So it gets reflected from the mirror, and we pick it up. So yeah. Previous slide, yeah.
Emitted by the source, it's reflected from the metallic plate.
Yeah.
Metallic plate is going to act like
a reflector. Yeah.
Now, I'm not able to get at what exactly is the need of doing the time reversal. Because, for example, if I have a normal sample, I have a source, I have a receiver. I know what exactly is the, basically I'm receiving some reflection from there, whatever that S parameter I'm receiving.
Yep.
Now, once I know that what exactly these S parameter for a not, you can say, not defect or undefected sample, when I replace it by a defected sample, it will not be the same.
Yes.
So I didn't get the importance of doing the time reversal.
Well, what you're looking for in this is actually, how do you image, you know that you can detect it, that's it, right? You can detect by looking at the difference between a good sample and a test sample. Let's call this reference, and you have a test sample. There will be difference, and you know that there is a, you can detect differences, that's true. But in addition here, we want to find the location, the size, you can actually image it from this signal. It's not just a detection problem, right?
That is time reversed.
Yep.
And is that receiver is going to act as a transmitter.
Right.
And now that initially whatever was the source will be receiving the signal.
Yeah.
And wherever is the defect, that will be acting as
a source. For the perturbation field, it's a source. So that part. Yeah, it is true that you can see that you can detect it just looking at comparing the two. Okay. But one of the things that is, see, if there is a rough surface, if there is noise, because of the fact that in time reversal, you are taking into account the phase difference, because you need the phase difference in order for that wave to, it's like an constructive interference, right? So even if you have random noise, even if it's a noisy signal, the noise gets eliminated. Only the part component of the signal that is in phase will interfere and produce the thing. So I don't have, when we initially started out, that was one of the study we did, I don't have those slides, but you can give it a very noisy measurement, but you will get the, because of the phase relation between the receiver array signal, you can get the thing done. It's like synthetic aperture focusing, somewhat similar to that. Yeah.
Correct. That means the time reversal is at the same locations, then I can take the differences of the electric field intensity. Then it will, because I don't have to change the phase or anything, because whatever is being transmitted is being received here. Now that rather than you can say changing the signal and all that time reversal is helping in reducing you can say subtracting the phase at same instant of time itself. I mean to say, let's for example, here is
Yeah.
a sample. Here I am having a source. This is my source. Here is my sample, and here I am collecting it. So because let's say this is much nearer to the detector. Now whatever is the phase difference that has been created by reaching here, that now if I make this as a source, now that the phase difference is different now.
Yes.
That is being overcome by doing the time reversal.
Right, exactly, exactly. Yeah, I have, in the beginning when we started out, and one of the study that we did was effect of noise. And we saw for, signal to noise ratio even less than 1, because the phase relation is maintained, noise is random. It's a natural filtering of noise and focusing it back. So going to this, let me play this thing. This is the schematic of the test scenario. And this, I think, and there is a disbond. So when we do the back propagation, we don't put the disbond in that, okay? Where the receiver array is over there. So it goes, and it goes and focuses right at the disbond. It comes back to the source. And so if I look at the time integrated image, I will see what over here is right at the disbond location. And we looked at how accurate the location is estimated. And these are the composite and epoxy epsilon values and so on. Okay. So these are all simulation results. It's a pulse with some kind of a center frequency. Yeah. Yeah, that's known. The sample properties are known, but what we're only trying to find defects or disbonds. So we know you can also use it for evaluating the quality of bonding. Sometimes these things deteriorate, so epsilon changes, and you can do some things like that. Because I think if you go into metal composite joints, particularly in aircraft, they don't want to put rivet holes through that. It's going to be, so it makes it a lot lighter, but you have to be very, sure that the bonding quality is good. So how does the epoxy deteriorate? And to do that, maybe if you can estimate the characterize like you're doing, the epsilon of the epoxy layer, then that's a great application for the work that you're doing. If you can find, get some epoxy and do a study on how the epoxy, expose it to the elements and see how epsilon changes. So first you have got to determine a good epoxy and a bad epoxy, right? The epsilon, and then see if you can characterize the epsilon. So this is the experimental setup for looking at time reversal in experiment. So again, this is our setup over here. Pardon? Can you see that better?
Yeah.
Okay, so of course we didn't have an array. So we really had a single receiver that we had to move along an arch. So this is the pulse that was time domain pulse that is applied with this particular frequency content. Oh, okay. Okay, so this is your receiver array over here, this con. Where is this? The source is, transmitter is over here. I can't even see it. Okay. Okay, you are able to see it. It's gone. So, so this again is a schematic, the same schematic that we used in the simulation. So we had this groove in this Teflon What's the question? Okay. Can you read out?
Yeah. We have done a defect detection of GFRP using microwave in our lab.
Mhm.
Defects included are mild steel, aluminum foil, and Teflon tape. We could only detect the metallic defects. Why?
Well, it depends on what frequency they use, right? So, was it a far field? Was it a near field? It could be, yeah. The reflector metallic foil will probably produce a very strong signal. But if the defects are less than a wavelength, and if you did far field, you'll not be able to detect it. So it depends on
I don't know how to.
No. Ask her to unmute herself.
unmute and yeah.
Actually,
So, ma'am, she's telling far field 7 to 10 gigahertz.
Yeah. So if it's far field, then there is diffraction. Even I showed the GFRP 3 holes, and we could detect the biggest hole using in the far field. You will not detect it in the smaller holes because of the diffraction limit in imaging. If it's less than lambda by 2, you're not going to detect it. That's the holes. But reflected fields by the foil is detectable. It doesn't.
So that is why she was not able to detect this Teflon tape.
That also depends on the size of that.
So what was the size? Can you tell us? Are we audible to you?
Yes, you can unmute and talk.
2 millimeters.
So, it's the same problem.
She's telling yes, 2 millimeters. Is
Millimeters at megahertz, 7 megahertz per second, 7 gigahertz.
She's telling 0.45 millimeter thickness. We have unmuted you. You can ask a question also.
Okay, am I audible, ma'am?
Yes, you are audible.
The sizes used were 2 millimeter, 1 millimeter, 0.5, and 5 millimeter.
Yeah. What's the wavelength?
What's the
wavelength of your source?
we have used the sweeping frequency of 8 to 12 gigahertz.
10 to 12 gigahertz. So it is greater than. It's greater than a millimeter, right? The wavelength is must be about 4 or 5 millimeters or more. So
Actually, we have done by analyzing the reflection coefficient, that is S11 parameter. Only we have analyzed the magnitude of S11.
right. But you got this of at far field. Whatever measurement you did was in the far field?
A near field measurement using open waveguide or using open waveguide adapter.
If it's near field measurement, you should be able to detect that. You should be able to detect in near field.
By analyzing the magnitude?
Yeah. So I think I showed a slide in the beginning comparing far field and near field measurements of the same 1 millimeter, 2 millimeter, and 4 millimeter holes.
Okay.
And the frequency was much lower than what you are talking about. And even at that low frequency, we were able to detect the by using near field measurement. Near field measurements has no resolution limitation, right? Because it's more inductive and capacitive coupling. You're looking at the S21 parameters. So it could be just noise, or I need to look at the signal to determine what the problem is.
Okay, maybe because of the noise.
But in principle, it should be detectable at near field.
Okay.
Okay. Especially
we could detect the mild steel and aluminum foil defects.
Yeah, those inherently metal foils will produce a high signal to noise ratio.
Yeah. Yes.
Whereas holes, because the contrast between GFRP and air, the epsilon, is much smaller. So your signals are lower, but it should be there, if you do some processing and amplification.
Okay, I will check once more.
Yeah,
Okay, thank you, ma'am.
no problem. Okay. So we were talking about the experimental validation of time reversal imaging. So this is the same sample. We have a groove that is all the way down. So you have a metal backing at the other side. So this is your composite sample. This is this a defect, a disbond, and on the other side there's a metal backing. So these are the other things. These are the thickness of the sample is in terms of wavelength. It is lambda by 3. The length is 1 lambda, and so also the disk bond is lambda by 6. It's so really sub wavelength. Okay, and we did exactly the time reversal part. So basically, where was the thing? This was the setup. The sample is kept over here. And we did the source and array of receivers. Time reverse the receiver, signal, propagate it using the model, propagate the perturbation field using the model, and look at the integrated energy, and you look at you find the disbond. It focuses, comes back to focus at the disbond. And this is the entropy at each time, entropy versus time. This is the minima of the entropy. And at that minima, when you plot the fields, you once again see, at this point, you can see a much stronger focus of the fields at that point. Oh. Yeah. Oh, what? Sorry. I should be looking at this. I was looking on the split screen. Sorry. So this is the experimental results. This is the time reversed energy integrated over the propagation time through the sample. And this is the entropy plot. And we took the minimum of the entropy, plotted the fields at that instant of time. This that gives you the time. And you can get a much more focused image because you're plotting it at one instant of time. In this thing, you're plotting the integrated energy over all time. So these were the experimental results of time reversal imaging. Okay, so that's the basic method, and what we have in the next slide are more examples. This is an example of impact damage over here. So over here, I think we had a bunch of receivers around. The signal from a reference signal and the scattered signal from one array position. This is the defect, the perturbation signal, time reverse it, propagate it backward. And this again is your time reverse energy image. So we could see the impact damage over there. And we got the same thing from a near field. You get a much better, at 12 gigahertz, you get very good. But it takes a much longer time. There's the magnitude and there's the phase image of the S21 parameters. But it takes a much longer time for this thing. Well, I shouldn't compare the time right now because time reversal is the simulation that takes time too. Okay. So, well, these are, early days. We can, at this point, we're just looking at feasibility, whether this kind of an approach is feasible. That's all we're looking at. And again, so this is our the GFRP sample with 3 holes, did the time reversal imaging. We're collecting it at a real large standoff distance, the receiver image, and propagating it back. We can see the large one, the next one, but the smallest one is not seen at all. Whereas if you do near field imaging at 12 gigahertz, you can see even the small one. we do some image processing, you can get better image. This is a near field. This is far field.
Both are same frequency, 20.
Yeah. See, the far field, you only have a center frequency, it's a pulse. So I can't say at this frequency. These are amplitude plots. Yeah.
Which gives better interpretation, the amplitude or the phase part?
I don't have an answer to that. I think we did try out amplitude, phase, magnitude, magnitude, phase, amplitude, and my guess is, this is a couple of years old, right? So I think the reason we went with this is because that gives the best contrast. Carbon fiber, yeah. For carbon fibers, carbon fibers will probably, I don't know how well it will propagate inside a carbon fiber composite because it's conducting. Yeah, but even this is glass fiber. Yeah, it's glass fiber with a metal backing. For carbon fibers, because of its conductivity, we have tried this. We have also tried simple open plate capacitance and capacitive coupling of electric fields inside the carbon fiber. And I don't have those things, but these were really, it was a blind sample. We didn't even know where the defects were. We could use coil and capacitive probe. It's basically a near field measurement. At that but much lower frequency, and we are able to penetrate a couple of layers. And these Teflon inserts were it was, I think, like a 12-layer laminated composite, a carbon composite, and we were able to pick up the different layers with that. We did at about 5 megahertz, pretty small, low frequency for not microwave by any stretch. Pardon? Size of the sensor is, yes, it can be large, it doesn't have to be smaller than the defect or anything. It can be, but as long as you have, it is large enough, because you need a little bit larger for the low frequency to pump enough energy into the sample and get the reflected energy back. So the size, because it's near field measurement, the size was immaterial, you could still detect that. It was eddy current or inductive coupling, is the same. We just tried out different things. We're just getting into NDE of composites. So carbon composites of quarter-inch thick, multiple layers. We just wanted to first see whether we have the ability to do NDE of composites. So that's our first shot. All MATLAB. All the FDTD model, we developed our own, and it was 2-dimensional, so we did just MATLAB. And developing a MATLAB code, FDTD code, is one of the homework assignments for senior students, right? So it's doable, so pretty fast. So I think this is so what we talked about. Let me just summarize. Principles of microwave imaging, ND. What happened here? Okay. The time reversal algorithms is one of the methods by which you can detect image defects in samples. So we showed the simulation results and also experimental validation of that. And the advantage is that it is pretty fast. Okay. So eventually, with computing resources, the computation time is going to be is not something that is of concern to us. But we can do rapid. One of the things that industry wants is, can I do it? Can I stay on the ground and look for problems in a composite aircraft at a very large standoff distance? So that can be done. We didn't do that experimentally, but feasible. We feel that that's something that can be done. So one of the things we thought in the future we could do as a first step, do whether it's a wind turbine or do a far field imaging, detect something. Once you detect something, then you can do a near field image of just that location and get a more higher resolution image of the defect. So that's our plan. That was our plan at the time. But the other thing that we also, well, what I'll talk about in the afternoon is, in order to increase the resolution, enhance the resolution of far field images, can I use some kind of a lens to reduce the spot size and then do a better, the higher resolution imaging in the far field? Okay, so for that we use a metamaterial lens, and I think I'm going to talk about that in the afternoon. So if you have let's discuss other questions over here. Yeah.
Expand it. If you go for a higher band, KUKA band.
Oh yeah, definitely. We know that. But two reasons. Yeah, we can do that. But we had to do what was available to us in the lab. So that's why we went with this. But these are all scalable, right? Yeah, you can do that. But that can definitely be done. You're right.
Receivers have kept for other side of them.
Not if it is a metal composite joint, but if it's just a dielectric, you can, even if it's dielectric, suppose look at an all composite aircraft, you don't really have both side access, right? And I think in Srijan's work, what I'll show later on this afternoon, even if it's on the same side, even if you don't have a metal backing, he was able to, just looking at the scattered field, the portable differences in the scattered field, you can detect it. But you need a reference measurement and do this thing. So that's the next thing that in his defense, the question that everybody asked is, not every time are you going to have a reference measurement. How will you eliminate the need for reference measurement? So can we look at some kind of a differential measurement? That's the next step. Whoever is going to join afterwards is going to work on a differential, just have two antennas, receivers, and see whether we can look at the difference between, hopefully one of them is in the defect free, one of them is in the defect location, and see. And of course, at that time, that means the source also has to move with the receiver. Well, there are other issues, so anyway, I won't get into that. But that's a problem, and there are ways to, there are issues in this current work that we need to work on still work in progress.
Antenna or any
Was in some, I think it was a horn antenna is what we used.
protection also.
Yeah.
We kept many receiver points. Get any more clarity.
Well, we are having an array of antennas right now. We simulated an array of antenna, a large aperture, by moving the a single, we don't have the resources. We don't have a great, to have a setup, experimental setup for this is going to require more resources. And in the US, we don't get any funding from the university. We have got to write proposals, get money from the sponsors, buy all the equipment ourselves, okay, out of research grants. So that's one of the problems that we face too over there. Yeah.
Ma'am, I have a doubt.
Sure, go ahead.
Ma'am, you have said that if the size of the defect is less than lambda by 2, it is not possible to detect, right?
In the far field.
In the far field. Oh, in the near field, we can detect
In
the
the near
defect of.
field, yeah, the near field does not have the diffraction limits. You know, when you
Okay.
have in the far field, when the physical energy is traveling like a wave, then you have the lambda by 2 resolution limit, right? I think I have.
Okay, ma'am. You have said that the polarization properties of E and H field have good sensitivity than the reflection properties to detect the defects.
Can you repeat that? Couldn't catch that.
You have said that the polarization properties of E and H fields have good sensitivity to detect defects.
Yeah.
Okay. Instead of scattering or instead of transmission or reflection coefficient measuring, is the polarization properties will give good result?
Polarization of the E field.
Yeah, yeah.
Isn't that same question?
Yes, sir.
Yeah, yeah, definitely. I mean, that was one thing that I mentioned in the beginning, that those are other features of electromagnetic waves and that should be exploited. And I haven't really done that over here, but that definitely can be done. And
Okay, okay, thank you.
yeah, so I don't know exactly what you'll get, but definitely if you optimize your polarization direction, you're going to get, we can enhance the signal to noise ratio. Good point.
Will not be able to get the defect size.
Yeah.
Configuration of the size profile of the defect.
In fact, I'll tell you what. See, this was actually a kind of sizing, a crude sizing attempt in terms of, if we look at the cross range signal across that, the half width, what is it? Half width at the full maximum half width thing, this dimension is sort of related to the actual Lisbon length. So that's one thing that we did. So we can look at the final image and come up with a feature that is correlated with the defect size at that one location. There is, as I mentioned, this is still work under progress, it's initial thing, but actual reconstruction of the profile, particularly when you have a full damage, impact damage. This was the energy image. So I want to go from here to see if I can process this to get the exact shape, size of the damage. But that needs to be done. It's not been done yet. And again, this is the near field measurement, which probably is closely related to this. But can we take this image and estimate the impact damage size? So that's the thing that's remaining. Right.
It's perfectly fine.
Yeah, yeah. You feel, as expected, we will get, but there are, you have to be in close proximity to the sample. That's the main thing.
That's
Yeah, and that takes longer time too because of that. See, the other thing we did is the time reversal imaging. If you're in the far field region, how many readings, how many antennas do I need in my receiver array? What is the minimum number of antennas we can still reconstruct? So those are the kind of studies that Saptarshi's thesis will have, and I'll send that to you. So we did a lot of parametric studies of how to optimize, how to minimize the experimental requirements, minimize the complexity of your experimental setup to get the results. So that's offline. Offhand, I don't remember exactly, but those are the things. Those are the things that's of interest to industry. We want to spend less money, get more information. Right?
Microwave and how to microwave at that particular location.
Yeah.
It goes more than 1200 degrees. So, is there any device to concentrate microwave at the desired location?
There are a simple lens will help focusing. Okay, you can use a dielectric lens. That's one thing. The second is if you use an array, you are familiar with synthetic aperture radar, synthetic aperture focusing technique. So if you have multiple sources, you can adjust the phase relation between this. It's pretty similar to what we are doing in time reversal, and so to bring it to focus. In the afternoon talk, I'll talk about metamaterial lens for focusing. Also, maybe that will help. Okay, but you can focus with dielectric lens too, right? You
Just the wavelength for different sources so that they converge to a point, just like what a lens.
yes, like any of yes.
2.45 gigahertz.
Mm-hmm. You will have to get I think you should look into the availability of lens and that frequency. I think it should be possible. That's I don't know. Not having worked a whole lot in microwaves, but I know that you have even we used a lens in our experimental setup.
And temperature.
That is one.
Oh.
Yeah.
In 100
But the
degrees
temperature is at the well, is not at the lens, right?
particular location where we have to wait, the temperature will be around 1500 degrees.
Right.
Inside that complete microwave,
Oh.
temperature will be quite higher.
Okay, so everything is in a chamber that itself is at higher. Yeah, then it's possible. Maybe we can look at the metamaterial lens. I mean, I don't know why it should operate.
Metallic,
There are, what's the temperature you said?
It was around 1500 degrees.
Oh, okay. I don't know. Yeah, even with the metamaterial lens, I don't know because it's got copper in the unit cells, a lot of copper in it, and that's going to vary. The temperature is going to affect the performance of that too.
How far we can keep so that the focusing is there, but the temperature effect is not that much.
Right. Yeah, and also the spot size has to be small, so you can't go too far away outside, and you've got to. Yeah, it's a lot of challenge over there. So what you're using microwaves?
In problem, find the perfect spot.
Yes. Right.
Even on the very small shape.
What's your spot size? What's the size you're talking about?
I'm talking about that is 0.5 mm.
Thickness. Not the thickness, what the weld.
Bed size is 25 mm to maximum 5 mm.
Oh, it's a large. The XY is pretty large. So you don't have, yeah. So what frequency are you using right now?
0.45 mm.
Hmm. Hmm. So it's a metal well, all metal. Well, if you go to slightly lower, higher frequency, you should be able to do it because it's not that small as I imagine. It is 2 millimeter, 2.5. Yeah. Yep. Say it again. This one. This one. Yeah. The setup that we use is we have a source antenna. You have a sample. The sample typically has a composite and a metal backing. So the source and the receiver array is also in the same side. Oh, the reason it has a metal backing is because when we started out, it was for determining this bond between metal and composite. See, this was again funded by automotive companies. So we were where they were lightweighting using metal and composite. So when they bond it, there was this bond. So that is why we started with the metal backing. And nobody had ever done time reversal with reflected waves. So when you have metal backing and you have a source here and a receiver array over here, can I look at these signals and estimate the disbond, whether detect a disbond, so on. So that was it was just driven by the funded project. It is dielectric. It's a see if where is the thing? Okay, yeah. So this is a schematic. So you have a composite material, you have a metal over here, and then you have an epoxy layer, and then you have a disbond. Okay, so that is what we are trying to. That was our end goal, to detect that. This one, yeah. It's not a particular frequency, it's a time, it's a pulse. Yeah. So once we have an incident wave, you measure the signal at all these arrays, array of receivers, okay, and then we time reverse these signals. We we have some reference signal too, so we calculate the perturbation signal from a test setup, time reverse the antenna signals, and no crosstalk. Yeah. I back propagate, right? I time reverse and back propagate using the model. And you back propagate it for a couple of milliseconds till it has gone past the sample.
I found this on the web.
This thing keeps listening all the time to what I'm saying. Yes, we are back propagating not experimentally, but using a model. And in the model, it's a clean sample, there's no defect. But the equations, when you back propagate, if there is, because it's a converging wave, right? It will keep going. The waves keep. I also had. I have a video. If there is no defect, you'll see that these back propagated waves just keep going. No, it doesn't focus. But if there is a defect, it will focus because we are looking at the perturbation. It's because when you have an array, okay, which has received the signal from a defect, and they all have a phase relation, and that's, is a wave phenomena. And that phase relation is very critical for imaging. And because, if you look at even synthetic aperture radar or synthetic aperture focus, it's the same thing. They have a large aperture by looking at an antenna array. They will manually change the phase to see, that's not done for detection, but for imaging. Okay. Anyway, so in this sample, I've not shown any metal at all. It's just transmission, that's all. But if you go to my, yeah, if you go here, there is a metal, and that is why, no. You can't, the metal is this line, there's a line here. Okay, let me do, yeah. There's a line over here, and that's why you can see when you look at the waves, starting from the source, it keeps going, and at the metal it starts reflecting. And then it goes to the receiver array. Yeah. It's just the receiver array picks up the reflected signals, the perfect area as well as the defective area, everything. All the information is there in this array of these signals. In this particular example, there is no defect. It's just a metal. There's not even a composite layer. Yeah, yeah. It depends, right? Because the source is like this, and the source is reflected. That's why we have the source. You have a metal. If you look at it, it does reflect, follows Snell's law and everything, and then reflects it. That's how it would reflect, because depending on the angle of incidence, right? Then when you go time reverse and do that, let's see. Yeah. So time reverse and focus, it comes exactly. There is no defect sample, nothing. It's just source focusing. It focuses at the source with the same. There are no defects at all. So it's just a source estimation. No, in the near field, it's not a wave phenomenon at all. The wave is not. This diffraction limit is only true for a wave. Okay, it's true for a wave. The wave. I think I have some slides in the afternoon. I'll show what causes the lambda by 2 mathematically when you have a wave and in the far field. In the near field, you're just measuring the field in close proximity. Okay. When you have a source and a sample, and you look at your wave equation, there are two kinds of waves. There are propagating waves, and then there are evanescent waves. And the evanescent waves decays very, very rapidly. The evanescent waves has all the high frequency information, and you can actually show it mathematically. For higher frequencies, higher than a particular frequency, it's evanescent, and there. Which is high frequency information, is all lost when you do a far field measurement, because evanescent waves die. When you do near field, you are imaging the evanescent. So all that is mathematically you can show that, and I think I have all the slides to show that, but I'll go over it in the afternoon talk. No, the resolution is how fine is your scanning. To some extent, the size of your sensor. The size of your sensor definitely will play a role. And then using this a particular size, if you scan it very, very close, you get all the perturbations. It doesn't have those kind of limitations. Okay, well, 12. On to my next meeting, okay? And yeah, and I think some of your questions will be answered in some of the slides I have in the afternoon. Yeah, okay. Any more questions over there?
That we have discussed, yeah.
Okay, so then we'll reconvene at 2:30.